Hey guys, today we're looking at projectile motion. So it's a very particular application of quadratics. The first part is actually going to be a little bit of physics. If you want to just skip through to the problems, feel free to do so. But I'm going to show you where it came from. So if we're thinking about a projectile, that's something flying through the air. So what causes something to fall? I mean, if I throw something in the air, a ball per se, it's going to come back down, right? Why? Well, the only thing acting on it is gravity. So that's where we start. If we look at the acceleration, it's going to be our gravity. Okay. Now, we're in America. We usually use feet. So the acceleration due to gravity is 32 feet per second squared. Pretty much everywhere else, they're using meters, which is 9.8 meters per second squared. All right, we can derive the basic equations using a little bit of calculus. You don't need to know that, but so acceleration is just acceleration. That's where we're starting with. There's nothing more to that. To get our velocity, that's speed with direction. It's our initial velocity, whatever we start with, we call that v sub 0, v naught, plus whatever our acceleration is, times how long it's been accelerating. Okay. Now, this is not a quadratic, is it? It's linear. So that's not where we're going. We want to look at the position. So it's called integration, what we're doing here. If we integrate this one more time, our position, z, x, y, whatever. I'm using z because it could be in the horizontal and vertical dimension. So z, why not? That's going to be our initial position plus our initial velocity times how long we've been traveling. Now we have to take half of the acceleration times the time squared. Again, that's a little bit of calculus. So if we're thinking about it, we have to decide what's positive and what's negative. Generally speaking, we're going to call up positive and down negative. So our acceleration due to gravity is going to be negative 32 feet per second squared and negative 9.8 meters per second squared. So this part right here is always going to be one of the two following things. Let me go ahead and underline that plus sign too. If we're in American units, half of 32 is 16, so that's going to be negative 16 t squared. If we're dealing with metric units, half of 9.8 is 4.9, so that'd be negative 4.9 t squared. So you're going to see that in all of these problems. It's either going to be negative 16 t squared if we're dealing with feet, or negative 4.9 t squared if we're dealing with meters. And that is why you're going to see that every single time. Now, we are dealing with the mathematics only, so we're probably going to rearrange it into standard form. So this negative 16t squared is going to come first. And let's just look at the problems. So you're not going to have to derive the equations, but let's examine this equation here. It's negative 16t squared, because it must be in American units. Oh, hey, look, feet, and 90t. Or remember that coefficient of t here is your initial velocity. How fast were we going initially? 90 feet per second. So that's where they got this equation from. And they use h for height. Okay. Now, let's read what it's asking us to find. How many seconds will it take for the ball to reach its maximum height? Okay. That's not asking for us to find when it hit the ground, so we're not going to set that equal to 0 and just do the quadratic formula. The maximum, that should ring a bell, hopefully. Think about it. It's a soccer ball being kicked, so it's on the ground, it goes up in the air, and then it comes back down. Something like that. That's the path of pretty much anything in projectile motion. It's going to look like some sort of upside down parabola. We're looking for the maximum height. Well, that, if you recall, is your vertex. The y-coordinate would be the height, or how many seconds. So that'd be it's asking for how many seconds at first. So that'd be the x-coordinate, because it's t is time. So the t is actually your x here, and the h is your y. So how many seconds? Now, how do we find the vertex? Well, if you remember, you can do negative b over 2a. This one is written in standard form for us. They got the t squared and the t. C is 0, but we don't care what c is in here, so that's okay. That's going to be negative 90 over 2 times negative 16. If I do that, hang on, this is in my way. Okay, so let's do that. Negative 90 over 2 times negative 16. And we get 45/16. This is the one time we're going with decimals, people. Whenever we're dealing with measurements or monies, we got to round. Okay. So how many seconds? 2.8125. Let's see. 8125. So I'm just going to write that down. Oops. Seconds. This is 2.8125 seconds. That's an S. I'm trying really hard to make that look like an S. Let me even do it in a different color. Maybe that'll help. S. Just type it, whatever. It doesn't specify where to round it to. I'd probably say the 10th place, so I'd say about 2.8 seconds. However, whenever you're finding the actual height, make sure you plug in the full value. In fact, I'd suggest plugging in that fraction, 45/16. So negative 16 times 45/16 squared plus 90 times 45/16. So you're asking, well, what about, and yes, I'll show you in a minute. You indeed can do that. But everybody can do this, just plug in numbers. So that's how we're going to do it first. Oops, make sure you don't mess up typing your stuff. And we get another fraction, but again, we're going to be rounding. I'll write the whole decimal down, 126.5625. That is in feet. That's feet per second. So I'd round that to 126.6 feet. I will specify in your assessment where to round: 10th place, 100th place, 1 decimal place, 3 decimal places. All right, so some of you might have remembered something from whenever we're doing the vertex form. Mode 5.3 will get you your vertex. Negative 16, 90, nada. It gets us those x-intercepts, and it gets us our 45/16, which is 2.8125. And it gets us our 126.5625. So it does give you your vertex. So anytime it's asking about the maximum or minimum of a quadratic, that would be your vertex. Part C, give the domain and range of the function. You might be thinking, oh, it's a quadratic. The domain's all real numbers. Yes, if we're just looking purely at the math side of it. But we've got some context here. Okay. Would it make any sense to have negative time? No, it doesn't make any sense to have negative time. So 0 is we're going to start for our domain. And if you do the quadratic formula, that'll get you these pieces right. So this is the ground, right? So that's the ground. It's kicked from the ground, so it's starting on the ground, and it's landing on the ground. Well, we have to assume that. We don't like to assume things, not in physics at least. But if it's not specified that it's being caught or it's stuck in midair for some reason, it's going to hit the ground eventually, right? And we're assuming it doesn't fly on top of a mountain. I don't know, maybe somebody kicked it really hard. But we'll assume that ground level is going to be the same. 0. We'll call it ground level 0. Because it doesn't tell us anything else. I mean, the problem could actually specify 30 feet below sea level or something. Then we'd say negative 30 would be our ground level. This one does not. So we'll go ground is 0. So this is 126.6 feet off of the ground, however high the ground might be. So our intercepts, if we look at them, we get 0 and 5.625. Well, this is 0 right here. It starts on the ground, and this is 5.62. Is that what it says? Yeah, right there. So my domain is from 0, where it's starting, to 5.625. It does include those values, so I'm using brackets. My range, oh, it's going down forever, negative infinity, right? Does it go below the earth? It's not a magic tunneling ball. They didn't say it falls into a giant gopher hole. It's not going down the Grand Canyon. We have to assume, if not specified otherwise, that it starts at one height and lands at the same height. So we'll call that starting height 0. It's on the ground. Oh man, what's the maximum height? Oh, hey, didn't we? Yeah, we found that already, didn't we? The maximum height is this. So that is my range. So a little twist on the quadratics formula there. You had to realize what it equaled. The ground is 0. Unless otherwise specified, the ground is 0. So we found where it started on the ground and where it ended up on the ground. The quadratic formula, mode 5.3. Mode 5.3 also gave us our vertex, which gives us our maximum or minimum. Typically, these will be maximum because it's projectile motion, height, and the time it reached that height, and how high it actually was. Okay, let's look at the level. A penny is dropped off the Empire State Building. So when I was teaching physics, I'd always say, draw a picture, which is 1,000. So, okay, my drawing's a little bad. Obviously, my drawing's bad. I draw really bad. We'll make the Empire State Building a nice pink rectangle. Somebody's holding that, but it doesn't talk about that person. So we're going to assume they're laying down. And they're aiming at somebody else, apparently. their former boss. Reach out and drop a penny that happens to be bigger than his head. So it's 1,250 feet. Why is he laying down? Because it didn't say it's above the building. The building's that tall. Sure, so guy's laying down, dropping a penny off of it. That's this height, 1,250. This is the equation. So again, it doesn't matter what it looks like. In physics, you have to derive the equation. Here, they're going to give it to you. Now, here's the question. How long would it take to strike a 6 foot tall person? This guy's 6 feet tall. I should love my scale. This is 6 feet, and this is 1,250 feet. Perfect scale. So what do I need to set this equation equal to? The penny's not hitting the ground. It's, I'm guessing, hitting the guy's head, not his toe. Again, it doesn't specify. But we're going to assume it's hitting the top of the person, and then it might go all the way through and hit the ground. But first, it's going to hit the head. So that needs to be equal to 6. That's my height. So let's examine the motion here. It's going straight down. Now, whenever we're dealing with projectile motion, we're imagining a parabola. Well, it's not making a parabola here, is it? No, but it would if we started by throwing it up first and then it came back down. Okay, so that's, we're looking at this leg of the parabola right here. So it's going straight down, but that is part of a parabola. See? So we can still model it with our quadratic. And yes, there's air resistance and stuff, so it's not perfect, but it's actually really, it's a really good estimate. Let's see. How do I solve this? It's a quadratic. Make it equal 0. Notice it was dropped. So what was the initial velocity if you drop something? 0. That's why there's no b term here. There's nothing times t because there's no initial velocity. Again, it's feet, so that's why we got the 16 instead of 4.9. You need to know all that? Nah, you just need to be able to solve the dang thing. That's 0, that's 1244. So we get that. What is that? I don't know. It's about 8.8. Let's go 2 decimal places. 2 works. So 8.82. And that is in seconds. I'm sure it says that somewhere. It doesn't, but it's in seconds because I know that 16 is actually 32 feet per second squared. So this has got to be seconds, otherwise this doesn't work. Oh, it's a quadratic. I got another answer, and it's a negative 8.82. Okay. Yeah, no, this can't be happening, huh? If we look at the context of the problem, a negative time does not make sense. Sometimes it does, not this time. Remember how this is a quadratic, so that's why we got that negative time. So we're going like this. So whenever you first threw it up, it was at 6 feet. Then it went up some more, and then it came back down. Well, if we're looking at this entire parabola, and we're starting here, negative 8.8 seconds ago was also at 6 feet off the ground, except we didn't throw it up to begin with. We just looked at the other leg. But that's why we have that negative time there. So our answer is just this 8.82 seconds. And again, I will specify word around. A diver standing on a platform 25 feet above the pool. He jumps from the platform with an initial velocity of 10 feet per second. And again, you don't have to draw a diagram because you're not in physics. They give you the equation. Oh, hey, they gave you the general equation. Maybe you do want to know a little bit of physics. Standing on a platform, 25. He's standing on the platform and jumps. Technically, they should say he ran off, right, based on what they had. Anyway, dude's over here. Sure. He's about to do a cartwheel off the diving board. And it's 25 feet above the pool. So that's our initial height, 25 feet. Here's the pool down below. Hopefully it's not lava. He jumps at an initial velocity of 10 feet per second. So he's not just falling off, he's jumping off. So he's gonna have an initial velocity. He's gonna go up a little bit and then down. But he's starting at 25 feet with an initial velocity of 10 feet per second. So our x naught, or our what? We're using h. Okay, our h naught, our initial height, is 25 feet. Okay, well, they use s for starting point. Sure. His initial velocity is 10 feet per second. They use v. Really not good, but they do. Okay. And t is in seconds, time in seconds. We were looking for what we're looking for. Write an equation. Oh, they just want the equation. So plug in the numbers. H of t equals negative 16 t squared. Let's see, initial velocity of 10 feet per second. And initial height of 25 feet. So that's part A. Part B, use that thing to find the diver's height after 2 seconds. So I'm gonna go modify 3 and no, I'm not. What am I trying to do? I'm trying to find out how high he is above the pool after 2 seconds. Maybe he's even down below the pool, I don't know. What do? Plug in 2. Excuse me. Get your calculator, go to mode 1, type it in, be done with the dang thing. Negative 19. Okay, did I type anything in wrong? It's possible. Okay. So his height is negative 19 feet. Let's interpret that, assuming I didn't screw up somewhere. So he hits the water. And once you hit the water, you're going to keep going down, right? So again, we're making some assumptions here. The water is going to slow you down more than air, right? Yeah, so he'd actually wouldn't be 19 feet because we're pretending there's no resistance, so he's going to just float right through the water like there's nothing there. Doesn't really happen, but if it did, he'd be 19 feet below the surface of the water. That's what the negative indicates. Because this is our zero here, right? The pool's top is zero. Well, he went 19 feet below the top of the water. Hopefully it's a deep pool. Let me just triple check. I didn't type anything in wrong. No, okay. I like that. It's a little exaggerated, but yeah, okay. So negative 19 feet is your result. Huh. So this is your answer right here. It is okay to have a negative distance here because it's indicating that's below the surface of the pool. Last one. An astronaut on the moon throws a baseball upward with an initial velocity of 10 meters per second, letting go of the baseball 2 meters above the ground. Okay, so again, sorry, I lost myself. No idea where I was going. We're given the equation, so we don't have to worry about what this means. Now, an interesting thing they have here is that the path can be modeled by negative 8t squared. No. Oh, moon. Air on the moon. So on the moon, the equation is negative 8t squared plus 10t plus 2. On the Earth, it's negative 4.9t squared plus 10t plus 2. That's the acceleration due to gravity on Earth, well, half of it. Apparently, the acceleration due to gravity on the moon is 1.6. That's half of it, so it's got to be 1.6. I was thrown off for a second there. I thought it was on the Earth first. But notice it's the meters. That's why we're doing with the 4.9 and not the 16. So let's check it out. How much longer would the ball stay in the air on the moon compared to on the Earth? So we're trying to find out when it hits the ground in both these times. So ground level is 0. We just gotta let the ground be 0, all right? So on the moon, 0 equals negative 0.8t squared plus 10t plus 2. Multiply 3 with negative 0.8. Yeah, you might 0.8 if you prefer, it doesn't matter in the least. 10 and 2. We get this, which is 12.7. Let's see. That's just subtraction. Let's go 3 decimal places, just for funsies. I don't know. 12.697. We're rounding to the 3rd decimal place. That's a 6. The next number is bigger than 5. That goes into a 7. Or it could be, oh yeah, that's negative. That ain't happening, right? Yeah, negative, not going to work for us. So it didn't hit the ground before he threw it. He's just 2 meters above the ground, so, if it was following the full parabolic path, then It had been at 0, negative 0.2 seconds ago. Negative 0.2 seconds before he threw it. He threw it? Yeah, threw it. And then we have ER. Same exact equation, except we're changing the acceleration. So we're changing the coefficient of t squared, changing our a. The exact answer I said there. Everything else is the same. Change the a, hit the equal, 2.22. 3 decimal places 224. Or we get a negative answer of negative 0.1918. Can't be negative. Doesn't make sense. So what is our answer? Well, go back. What is our question? How much longer would it stay in the air on the moon compared to the Earth? So what are we going to do with these? Subtract them. And we're going to get 10.473. So let's go with 10.5. 10.5. There we go. That's a T, not an A. So the time is 10.5 seconds. All right. That's, again, how much longer would it stay on the air, in the air? There's no air in the moon. Interesting. Interesting expression. Anyway, sorry. How much longer would it stay afloat on the moon compared to on Earth? 10.5 seconds. Okay. So again, you're going to be given your equations. You don't have to derive them. But these A's, coefficients of x, well, t squared, came directly from the gravity of whatever planet you might be on. Everything else is initial velocity and initial position. So for your assignment, you'll be finishing the ones we didn't do. All right, that's about it. Yeah.